everybody, how are you? I hope you are doing very well. Today inshallah we'll continue our lesson about solubility equilibrium. So far guys, we have learned about KSP and how to measure or how to calculate KSP and how to calculate solubility product knowing KSP value, or how to calculate KSP knowing the solubility product. Today we'll know what we are using KSP for, guys. What is the benefit of KSP? Actually, KSP value is used to predict precipitate formation. So guys, as you know, substances differ greatly in their tendencies to form precipitates when mixed in different concentrations. So as you can see here, this figure, this photo shows us the behavior of some anions in the presence of certain cations. Okay, so we can see here that in certain or some test tubes there is no precipitate, while in others we can see the precipitate fall out of the solution. So for example, in A we have a solution of silver nitrate. Silver nitrate is highly soluble and it will produce the silver cation and nitrate anion in solution. So here no precipitate forms, but in B, adding silver nitrate, which is, as we said, highly soluble, to a solution of potassium bromide causes precipitation of silver bromide, as you can see here, the white precipitate. In C we have the same, guys. We have potassium iodide and lead nitrate. Both of them are soluble, but when they are mixed together, a compound called lead iodide will form, and it will form precipitate, and it will fall out of the solution. Okay. In D we have here potassium chromate. Potassium chromate is an exception because most of the chromates are insoluble, but potassium chromate is soluble. But when potassium chromate, the soluble potassium chromate, is added to silver nitrate, which is also soluble, silver chromate precipitate will form. Okay, so in E, for example, we have sulfates. We have barium sulfate, guys. Well, sulfates are generally very soluble. Okay, so barium sulfate is an exception to the rule. Adding barium containing compounds is often a test for the presence of sulfate ion. For hydroxides, guys, all hydroxides except for a few are insoluble. For example, here we have nickel hydroxide. Nickel hydroxide is insoluble. Or a nickel hydroxide, actually the precipitate will form when you mix what? When you make a solution of nickel chloride and sodium hydroxide. Okay, so nickel hydroxide, the precipitate will form. So guys, the equilibrium condition doesn't require that the two ion concentrations be equal. The two ions that will be released from the certain compound. Equilibrium will still be established so that the ion product doesn't exceed the value of KSP for the system. So what do you mean by this, guys? Suppose we have, let us take barium carbonate as an example. Barium carbonate will dissociate according to the following equation, guys. Barium carbonate will dissociate to give us 1 mole of barium cation and 1 mole of carbonate anion. Okay, so 1 mole of barium carbonate will dissociate into 1 mole barium and 1 mole nitrate ions. Okay, so the concentration of the two ions, the barium cation and the carbonate anion, were equal. However, guys, equilibrium condition doesn't require that the two ion concentration be equal, as we said, and here equilibrium will still be established so that the ion product, I mean the concentration of barium and the concentration of carbonate ions, doesn't exceed the value of KSP for this system. So if the ion product is less than the value of KSP at a particular temperature, then the solution is unsaturated. But if the ion product is greater than the value for KSP, I mean the concentration of the produced ion is greater than the value for KSP, solid precipitates. Okay, so here, in order to predict if a precipitate will form a certain reaction system, we need to find out the concentration of the produced ions, and then we will see if the concentration of these ions is greater than the value of KSP, then we expect that solid precipitate. Okay, so guys, suppose that unequal quantities of barium chloride and sodium carbonate are dissolved in water, and the solutions are then mixed. If the ion product, the barium and the carbonate ions concentration exceeds the KSP of barium carbonate, then, as we said, a precipitate of barium carbonate forms. After precipitation, the ion concentration are such that barium concentration and carbonate concentration equals the KSP. So, as we say, the solubility product can be used to predict whether precipitate forms when two solutions are mixed. We will find out the concentration of the ions. If the concentration of the produced ions is greater than KSP, then precipitate forms. Okay, so guys, let us try to answer sample problem D together. The question is, will a precipitate form if 20 ml of 0.010 molarity of barium chloride is mixed with 20 ml of 0.0050 molarity sodium sulfate? Okay, so again, what is the plan here, guys? To know if a precipitate will form, we need to measure the concentration of the ions that will be released in this reaction system, and then we will compare their concentrations with KSP value. If the concentration is less than the KSP, then precipitate will not form. If the concentration is greater than KSP, then precipitate will form this reaction system. So guys, here what do we have? As a given value, we have concentration of barium chloride solution. We have also the volume of barium chloride solution, which is 20 ml, and here, guys, we need to convert the volume into liter. How? Dividing this value by 1000. Okay, concentration of sodium sulfate is known, and volume of sodium sulfate is known as well, 20 ml, and again we need to convert this value into a liter. Okay, unknown is whether precipitate forms. Okay, solution: the two possible new pairings of ions are sodium chloride and barium sulfate. Okay, as we know here, guys, barium chloride with sodium sulfate. What do you expect the products will be? We need to make what? A double substitution reaction. Okay, so we'll get sodium chloride and barium sulfate. Guys, we know that sodium chloride is highly soluble, so it will not precipitate, while for barium sulfate we need to, according to our calculation, we will find out if barium sulfate is gonna form precipitate or not. Okay, barium sulfate is sparingly soluble salt, as we say, sparingly, and it has a limited solubility. Okay, so now, first of all, we need to write the our equilibrium equation, our balanced equilibrium equation. Barium sulfate, the solid, will dissociate and yield barium and sulfate ions. Okay, 1 mole of barium sulfate will give us 1 mole of barium cation and 1 mole of the sulfate anion. Then we will write the expression of KSP. KSP, as we said, is equal to the concentration of the ions raised to the coefficient that is equal, or raised to a power that is equal to their coefficient. So KSP expression will be this way, guys. KSP is equal to concentration of barium cation multiplied by concentration of sulfate anion. And from the table, guys, we have KSP is equal to 1.1 times 10 to negative 10, guys. Here the Turkish yumuşak means negative. I don't know why it just keeps showing up this way. Anyway, now, guys, once you write the balanced equation and the KSP expression, we need to find the number of moles of barium and what the sulfate ion. Okay, so, guys, we know that here we have the molarity of each of the solution. From the molarity, we can find out the number of moles of the ions that will be released. So here, okay, as we know, guys, okay, so you may remember that we discussed about the molarity, and we say that molarity is equal to what? Molarity is equal to number of moles, okay, number of moles over what? Over volume and liter. Okay. So molarity is equal to number of moles over volume in liter. As I said, we need to convert the volume to liter, and then since we have the molarity for each of these two compound, we can simply calculate number of moles. Number of moles will be equal to what? Molarity multiplied by the volume, as you can see here. Moles of barium ion is equal to 0.020 liter multiplied by 0.010 mole of barium ion, and will be equal to this value. Okay, what about the sulfate ion? Will be the same, guys. Number of moles for sulfate ion is equal to what? Volume multiplied by the molarity, and will be equal to this value. So now we have the number of moles for each of these ion, for the barium and for sulfate ion. What next, guys? So now, since we mix both of the solution together, guys, we need to find out the total volume of the solution. Total volume of the solution. Okay, so for the first solution, for barium chloride, it was 20 ml, and for sodium sulfate, it was 20 ml. Okay, so here, after you convert the value into liter, we just need, as I said, to find out the total volume of the solution that is made up of the barium chloride and the sodium sulfate. Okay, and it will be equal to 0.040 liter. Okay, so now we need to find out the concentration of the ions. The last step, find out concentration of barium ions and sulfate ions in the combined solution. Okay, to find out the concentration of barium, you simply need to divide the number of moles by the volume of the solution. So remember, we calculated number of moles of each ion. So here you just need to divide each of the concentration of each of the value that we calculated by the volume of the solution. For barium, number of moles that we calculated was equal to this value. So now concentration of these ions will be equal to 5 times 10 to the negative 3, okay, mole per liter. The same will be for sulfate ion. Concentration of sulfate ion in combined solution is equal to what? The number of moles of the sulfate ions divided by the volume of, or total volume of solution in liter, okay? So here the value will be equal to 2.5 times 10 to the negative 3 mole per liter of what? Sulfate ion. So now guys, we have concentration of barium ions and the concentration of sulfate ions. We need to multiply these two values by each other, okay, and then we will compare the final value with KSP. Okay guys, so 5 multiplied, or 5 times 10 to negative 3 multiplied by 2.5 times 10 to negative 3 equal to 1.2 times 10 to negative 5. This value we need to compare it to what? To KSP value. KSP value, you remember we said KSP value is equal to 1.1 times 10 to negative 10. So the value, of course, this is the KSP value for what? KSP value for the solid barium sulfate. So as you can see, the concentration of these ions is greater than KSP of barium sulfate. Then according to that, precipitation occurs, okay? So again guys, as we said, we use KSP value to predict if precipitate will form in certain chemical reaction. So here we need to find out the concentration of the ions that will be released, and then we will compare it to the KSP value of the solid. If the KSP, or if the concentration of the ions is greater than KSP, precipitate will form. If concentration of these ions is less than KSP, then precipitation will not form. As you can see here, we learned how to find out the concentration, guys, for the ions. Let's go back again. We need to write first of all the balanced equation, equilibrium equation. Then we would write KSP, the KSP expression for this solid. We will find out KSP from the table, okay. Then guys, in this problem we had the molarity of these of the two solutions that is mixed together. From the molarity we can find out the number of moles of each of ions that will be released. We use the molarity of barium chloride to find out the number of moles and then the concentration of barium ions, and we use the molarity of sodium sulfate to calculate the number of moles and the concentration of sulfate ions. After that, guys, we just multiply the concentration of these ions by each other, and then we compare the value with the KSP value that we have, and according to that, guys, we find out that the concentration is greater than the concentration of these ions is greater than the KSP value, and according to the rules, if KSP is less than the concentration of these ions, then precipitation will occur, okay. So guys, last thing that we should know is limitations on the use of KSP. Okay guys, the solubility product principle can be very useful only when applied to solutions of sparingly soluble substances, and as I said, it can be applied very successfully to solutions of moderately soluble or very soluble substances such as sodium chloride, guys. The positive and negative ions attract each other, and this attraction becomes appreciable when the ions are close together. Okay, sometimes it's necessary to consider two equilibria simultaneously. So guys, this diagram summarizes for us how to use or what kind of problems we have learned, and what formulas we can use to carry out our calculations. For slightly soluble salt in water, salt to product KSV constant will be applied. The problem will use the following formula. KSV is equal to concentration of what concentration of the ions that will be released, each raised to the power equal to the coefficient of these ions. Okay. Other reversible reactions, guys, will apply equilibrium constant. In these problems, we will use the following formula. K equilibrium is equal to concentration of products over concentration of reactants, each raised to the power that is equal to their coefficient. Okay, so guys, that's all for today. Thank you, and see you inshallah tomorrow.